right, we're going to now talk about the relationship between our old friends, position, velocity, and acceleration, or more specifically, distance traveled versus distance traveled and speed and radial and tangential acceleration, things we've discussed before, and our new kind of angular kinematics quantities, angular position, angular velocity, and angular acceleration. So the first thing we want to address is if we have an angle, if something has moved, so I'm going to look at this point, the dot that's on the outer rim of the circle, if it's moved through an angle theta, or in other words, this whole thing has rotated around the axis here by an angle theta, how far has it moved in terms of distance? What is the change in the arc length position? In other words, what would this distance I'm calling delta x right here? How big is that? And we can get that from just the definition of this angle in radians. We would say this angle in radians is nothing more than delta s over r, and we can use that to solve for delta s. That's exactly what we wanted. So this relates an arc length to an angle, which is sort of like a linear distance being related to an angular distance or angular displacement. That's a relationship between an angular and a linear quantity. All right. Well, one thing we have to keep in mind is that depends on where the thing on the object is. In other words, what R are we using here? Well, it's the R appropriate for whatever we're interested in. I happen to show one. This happens to be on a disk that's of radius R. And if I'm interested in a point on the edge of the disk, that's the appropriate R to use in here. But if I'm interested in a point that's not out on the edge of the disk, of course, the R I should be using is the distance that the point I'm interested in calculating that delta S for, the distance it is away from the rotation axis. So R might be small like this. And you know, many times we won't even be talking about a circular disk kind of object. In general, we could have some strange shaped object that, you know, you can imagine this is made of some cut out sheet of plastic, and it's got a fixed rotation axis, so it's rotating around this point. And as this thing rotates around, this point on the tip of the piece of plastic is going to go around in a big circle. This whole thing's going to rotate around in a circle as time goes on. In that case, there is no radius of the disk. There is no disk in this case. So when we're talking about a point on there, the R we're going to use in this relationship is how far that point is from the rotation axis. Now what we're interested in is the relationship between speed and omega. In other words, let's imagine this thing is rotating in this direction and ask ourselves, what is the speed at which this is traveling if it's moving at an angular speed omega? Let's first do just something that has to do with angular rotation, a voting question. Ladybug sits at the outer edge of a merry-go-round, and a gentleman bug, my apologies, I didn't write this particular question, sits halfway between her and the axis of rotation. The merry-go-round makes one complete revolution each second. How is the gentleman bug's, that's this one in here, angular speed related to the ladybug's? And the answer is it's exactly the same. An angular speed just tells us how fast that whole rigid body is rotating. So any point on it is rotating at the same angular speed, 1 revolution per second. It's the linear speeds, you know, the good old-fashioned just speed. We don't say angular, we mean the speed we've been talking about. And their speeds would differ, but their angular speeds are the same. So again, we're concerned with that speed there and how it relates to omega. And the very definition of the average velocity, or how fast something is going, is just how far it moves divided by the amount of time it takes. So let's start out with that definition. And now let's use our recently acquired piece of information that how far it moves can be related to the angular displacement, or how far this thing has rotated in angles, just using that relationship up there. And now we know by definition delta theta over delta t is by definition the average angular velocity, right? That's what we said in the previous video section. Delta theta over delta t is what we call the average omega. So I've just factored out the r there. We're left with the average omega. So that tells me a relationship between the average speed and the average angular velocity over a certain period of time. And of course, we can take that period of time to be really small, and that would give us the similar relationship between the instantaneous speed and the instantaneous angular rate. So v equals r omega. If you know how big omega is, then your v depends on r, right? At a certain omega angular rate, things that are far out are rotating at higher speeds, whereas things that are closer in, smaller r's, are rotating at smaller linear speeds. Okay? Similar question. What about the acceleration of this point? This thing's rotating around. Well, this point is certainly going in a circle, so there's going to be at least some centripetal acceleration. And if it's speeding up or slowing down, then there might be some tangential acceleration. So we're going to think about that too. First of all, I have, I think, a couple of voting questions, perhaps related to the previous idea and to acceleration. Here's a situation where we have a puck of mass m that's moving along at speed v in two different situations, and we got a similar puck of mass m which is attached via a string to a little pin there so that you can spin that puck around in a circle. It's on a frictionless tabletop. Okay, and they both collide elastically, and in this case, remember, elastic means kinetic energy is conserved. After the collision, this second puck is rotating around the pole. Suppose we lengthen the string by a factor of 2, in other words, the right one compared to the left one, and repeat the experiment. How do the angular speeds in this situation compare to the one on the right? So think about it for a second. The answer is the angular speed is half as big in this case, and that's because, as this is sliding along, if momentum is conserved and it's an elastic collision, one of the cases that you're familiar with from billiards is if you have a ball sitting at rest and you hit it with the cue ball, that's pretty close to an elastic collision. What happens is the two exchange velocities. The cue ball comes to rest and the other one moves on with speed v. So this would be moving with speed v, and in this situation, this one would be moving with speed v in the upward direction just after the collision. In any case, it doesn't matter what the speed is. They're both moving with the same speed after the collision, and then their velocity direction starts changing as they move around in a circle. Their speeds are the same. What does that mean about their omegas? Well, if they have the same speed, whichever one's at a smaller r is going to have a bigger omega. We can get that from our relationship over here. If we solve for omega, omega is equal to v over r. Whichever one is moving on the smaller radius, if it has the same v, will have a bigger omega. So in that case, this one has a bigger omega, so it's twice, the angular speed in the first situation is actually going to be twice as much. I've marked the wrong one here when I went through and marked these on. In the first situation, this one here, the angular speed is going to be twice as big as the second one, so it should say twice as high. I just highlighted the wrong one there. Second voting question, and Ladybug sits at the outer edge of a merry-go-round that is turning and slowing down, and since we're going to start talking about radial acceleration and tangential acceleration, this is just to remind us. At the instant shown, this is the direction that it's rotating around the fixed axis in the center. At the instant shown, the radial acceleration of the ladybug is in which direction? And the answer is it's in the minus x direction. It's centripetal. It points towards the center of the circle. Okay? Similar question. The tangential acceleration of the ladybug is, and we've got to read this again carefully, it's turning in the direction shown, but slowing down. And in this case, if it's slowing down, the correct answer is its tangential acceleration is in the minus y direction. In other words, back behind the ladybug at this instant, because if the tangential direction is in the same direction it's going, that means the ladybug's speeding up as time goes on. If you're accelerating tangentially in the direction you're moving as you go in a circle, you're speeding up. Whereas if you're accelerating back against the direction you're moving, you're slowing down. So in this case, since it's slowing down, it's the tangential acceleration would have a negative y component, in other words. All right, back to the task at hand. We're going to start saying I'm going to concern myself with this point at this instant in time as this thing is rotating around in this direction. So the radial direction we'll say is radially in towards the axis of rotation, in other words, towards the center of the circle that this thing is moving on. And tangential direction is in the direction tangent to the circle, so at this point that would be in the upward direction. And the question is, what's the acceleration of this point? In other words, what are the tangential and radial components of the acceleration? Let's use the fact that we just reminded ourselves, the tangential acceleration component, when something's in circular motion, not necessarily uniform circular, but just any circular motion, tangential acceleration tells us how fast the object's speed is changing as it moves in a circle. And so we can write the average tangential acceleration is equal to the change in the speed divided by the change in time. And we already know the speed is related to omega by v equals r omega. So delta v is going to be r times delta omega. And delta omega over delta t is the average angular acceleration. That's a definition we gave previously. So therefore, if this is true for averages, average tangential velocity is equal to the average r times the average angular acceleration. That's true at any instant of time, but just by taking a very short time near the point that you're interested in. The tangential acceleration is equal to r alpha. What about the radial acceleration, or we might call it centripetal? Centripetal and radial components mean the same thing. Radial point for us is going to point toward the center of the circle compared to the point we're interested in finding that radial component. As we talked about in non-uniform circular motion, this is still, it's always v squared over r, even if you're in non-uniform circular motion. The radial component doesn't change, it's the tangential component that changes. So it's v squared over r. If we substitute in v equals r omega, that's r omega quantity squared over r, and then we square it out. We get an r squared omega squared in the numerator, and one of the factors of r cancels with the denominator, so we're left with just the radial component of the acceleration is r omega squared. Here it is written in terms of linear quantities. Now we've got it expressed in terms of angular quantities. So this is the relationship between linear acceleration components and angular quantities. Now, in all three of these expressions, because we assumed up at the top, and all of that assumption went through the rest of the slide here, we assumed that theta was measured in radians. Otherwise, this relationship wouldn't be true, and this one wouldn't be true. We use that relationship in the derivation of this one, and we use that relationship in the derivation of this one and this one. So in all of these, we have to, if these are going to be true, we have to use radian units for the angular quantities. In other words, theta has to be measured in radians. If for this to be true, omega has to be measured in like radians per second or radians per minute, but no degrees or anything. And alpha has to be measured in radians per second squared. This omega has to be measured in radians per second. Otherwise, we can't use those. They would be slightly more complicated. And that's just what this is reminding me of. So those four relationship have to use radians units. Finally, let's talk about constant alpha rotational kinematics, which is very, very similar to constant velocity linear kinematics. In other words, if we assume the relationship between theta and omega and alpha is exactly the same as the relationship between x and vx and ax. We made all the similar definitions for those. And that means that if we assume, just like we assumed constant ax over here, and we were able to derive these three equations using calculus, we didn't derive them, but that's where they come from. Similarly, the assumption of constant alpha, or constant angular acceleration for an object rotating around a fixed axis leads exactly to the analogous angular equation. So notice what the change is here. Every x that we have in the ones we're familiar with becomes a theta. Every vx in the ones we're familiar with becomes an omega. You know, if you have a subscript 0 there, we put a subscript 0 there. Every ax becomes an alpha. The change in x or displacement there becomes a displacement in angle. So all of those, you don't have to really remember these new equations. They're the same as these ones. We just substitute, for every linear quantity, we substitute the corresponding or analogous angular quantity. And let's practice with using those. So things don't always move with constant angular acceleration, just like things moving along the x-axis don't always move with constant linear acceleration, but it's common enough that it's worth practicing with. So let's try a problem, and let's do all of problem 1, I believe we are supposed to do here. I'm not sure if that's just parts A, B, and C. A grinding wheel is initially spinning in the counterclockwise direction, so we're imagining we're looking at it from the side and it's moving opposite the direction of a clock at 1,000 RPM. At time t equals 0, the power is switched off, and it takes 12 seconds for the grinding wheel to come to rest. We'll assume it's coming to rest, so it's spinning an angle, right? And it's slowing down as time goes on, so that means it has an angular acceleration. And let's assume that angular acceleration is constant. Let's call the counterclockwise spinning direction positive and answer the following questions. The angular velocity at t equals 0, the wheel's angular acceleration, and the wheel's angular velocity 3.7 seconds after flipping the switch off. So we'll be back with the answers to that one.